All right, I think we can start, and let me start again by thanking Anna Maria for a wonderful and a very nice set of lectures about this new topic. And now we have the last discussion session where the last questions about celestial holography can be asked. So let's see, what is your plan? Did you prepare something or?
Yeah, I mean, I did prepare something, but I was also hoping that people would ask questions. I could talk, well, there are some options, but I was going to talk about this recent work by Guevara, Himwich, Pate, and Strominger, and they had a very recent paper about this algebra of soft currents. I could say a little bit about that because it ties nicely into the last thing I discussed last time about celestial symmetries. But if people want to ask questions instead, or they want me to talk about something else, like, I don't know.
Yeah, let me maybe ask a question and then we'll see if there's any discussion or maybe we can indeed listen to the speaker about soft focus. It's actually, I have a naive question. So you explained how the celestial amplitudes are naturally, let's say, are in representations of conformal symmetry. But so they are some transformation of original amplitudes, and how do you determine the original amplitude? That was my question. So I think in the case of three-point amplitude, it was just basically a coupling constant or something like that, and then you're completely transform that.
Are you asking, given the celestial amplitude, how you determine the original amplitude, or?
Well, what is the original amplitude? How do you compute it? Does it depend on the theory or?
Well, yeah, I mean, of course, the original amplitudes depend on the theory. And if we were all, well, there is this one-to-one map between scattering amplitudes in flat space and celestial amplitudes. And even if we know a lot of things about amplitudes, I think our knowledge is still very limited, right? I mean, most of the things we can say about scattering amplitudes in flat space, I mean, we know a lot of things, but most of them are perturbative. And so, of course, you can construct, the way I formulated the problem is that, okay, given a scattering amplitude in flat space, say we knew what it was, you can associate it with, you can construct from it a celestial amplitude, right? But of course, we don't know. I mean, as you're saying, we don't know what the scattering amplitude in flat space is. But one of the goals of this program, and perhaps, I mean, it has definitely not been achieved yet, but it's an important, interesting question to be asking, is whether one could start the other way around. So like, start with an object which is defined with some observable on the celestial sphere, which obeys some properties, like for example, is constrained by all of the symmetries I was talking about. Then, putting everything together, everything we know about these celestial theories, can we write down some function which obeys all of these constraints? And if so, then what does it correspond to in the bulk? So
then I guess the immediate question, let's say you have all these constraints for 3-point and maybe something for 4-point amplitudes. Can you derive some constraints for original amplitudes from that, or?
Yeah. Yes. So for example, say for this 4-point example I was giving, yeah, one can take, I mean, there is an inverse transformation one can do to derive the momentum space scattering amplitude. So conversely, if you have some function which obeys all of the constraints, if you're all powerful and knew all of the constraints, sort of perhaps like in a bootstrap kind of philosophy where, okay, we're imposing crossing symmetry and unitarity, and then we're able to sort of perhaps numerically or analytically in some regimes solve these constraints, and derive some correlation function. Say you had some analog of that for the celestial theory. Of course, it has not been fully developed yet. But say you had some consistency conditions, like some full set of consistency conditions, you could ask, okay, what are the solutions of these constraints? And constraints could be different. I mean, ultimately, we'd want to say something about gravity in asymptotically flat spacetimes. Perhaps, I mean, not something non-perturbatively, perhaps. So something about consistent theory of quantum gravity more generally. This is what you would wanna learn something about, perhaps. And in that case, I mean, right, once you have an object on the celestial sphere, which obeys all of the constraints you have worked out, and now they have to be obeyed, then you can see what the consistent solutions are. And from those consistent solutions, you can take an inverse Mellin transform. So maybe I haven't, let me just write it down. But so in these lectures, I was talking about the map from momentum space scattering amplitude. So say we have just massless scattering. The map is simple in this case. So we have a momentum space scattering amplitude. Okay, let me just be consistent. Q1 to Qn. And I said that, okay, we can construct this object, which is a Mellin transform of the momentum space scattering amplitude. So again, Qi is omega I, Q hat I of Zi and Z bar I. And this is what gives us the celestial amplitude. But say we want to work the other way around and say we have some constraints whose solutions are these A tildes. So conversely, then one can infer the momentum space amplitude. And this would be inverse Mellin. This would be given by the inverse Mellin transform. So oh, sorry. Delta I, and then I forget. I think it's something like. Okay, I need to think. Here it may be delta I minus 1, something like this. Or C. Okay, I need to. It's well defined. It's the inverse Mellin transform. So does that make sense? Does this answer your question?
Yeah, sure. Well, I mean, I guess the question is also what kind of information. Well, were you able so far to extract any information already? Some interesting constraints on the amplitudes, or does it look like a doable problem in general?
One example. Well, I think so far.
I think we learned a very nice example of light cone bootstrap in Mandalena's lectures, right? Some tricks like this.
So no, I agree. But one thing that, okay, so far, I don't think there is an example where we learned something we didn't know about from the celestial framework, but there is something I have not. So there is an OPE of gravitons. So in this last lecture, I talked about this OPE of gluons and how it's fixed by, how it's fixed by, to leading order, how it's fixed by the celestial symmetries, and there is an analog relation in gravity. So, sorry. So this is again C1, C delta 1, C delta 2, G delta 1 plus delta 2 plus, and this again can be determined from the sub-leading soft graviton theorem. And this, okay, plus other stuff, but this leading relation in the bulk maps onto collinear factorization in gravity. And this, from to prove collinear factorization in gravity from amplitudes methods, even with modern techniques, is not very simple. It's actually quite hard. And in fact, I think some paper by Byrne and collaborators, I forget now exactly. This was, I don't know, like 20 years ago or so. I think was this result proven, and it's a long calculation. It's not easy to do. Here, doing it using symmetries, it's like, I don't know, it's like 2 lines basically. You get this recursion relation, and then it has a solution. It's of a different, it's completely different nature. The 2 calculations are very different, right? I mean, the one from amplitudes, you have to write down some Feynman diagrams and then calculate them. And here, from this different symmetries are made manifest basically. And you know, there is these recursion relations which are implied by all of these, by translations and soft symmetries. And it could be that, you know, once we understood all of them, we could say, some other people have said things about subleading, about some subleading contributions to this OPE as well. And in particular, this thing I wanted to perhaps discuss a little bit about the algebra of soft currents exploits that fact. So exploits the fact that one can actually resum the contributions from half from the SL2R right part of the global conformal group into an OPE block, and then use that kind of resummed OPE to say something about the full tower of subleading and subleading and so on, soft operators. But of course, I mean, there is this algebra, and okay, touching upon this recent result by Andy, that it's upon, in particular in gravity, upon redefinition of these operators, one finds these W algebras, which, okay, I'm certainly, I don't know very much about them, but they have appeared in other contexts. And it would be interesting to understand, this is again, it's a very recent work, but it would be very interesting to understand how this relates to other kinds of results.
Okay, I think these are great examples. Let's see, I don't see any questions so far. So maybe you can indeed tell us a little bit more.
Yeah, so I can talk. Okay, I can talk a little bit about this work. So again, this is not, I'm also learning. It's not my own work. So if I make mistakes, I'm sorry about that, but I'm gonna try to see if I can explain what's going on in these 2 papers. So these are very recent, as you can tell. So from March and May of this year, respectively. And this is also to illustrate that the things I've been talking about in these lectures, it's only been 3 lectures, but I think one can actually understand some very recent papers. So, okay, we have a question. That's great.
Very good, Igor, please go ahead.
Oh, hi, hello again. I have not been able to do the calculations for myself. I have just started to read the literature, but consider, for instance, the scattering of two to two particles at 3 levels in the book theory. Then you want to express the momentum space amplitude as a celestial amplitude. So you do a Mealy transform. However, depending on the momentum space amplitude, for instance, a theory of scalar fields with an interacting term within a Lagrangian with a dimensional coupling constant, the momentum space amplitude will have a dependence on the power of the number of derivatives in the interaction terms or some given energy scale. So when you apply the Mealy transform, it is not possible to get a ill-defined, namely non-analytic celestial amplitude if you do not regularize the theory in the ultraviolet sector, in the UV. So what I am trying to raise is the following. The story starts with Schrödinger triangle in trying to understand the infrared structure of gauge theories. But now in celestial holography, it seems that the theory becomes sensitive from the ultraviolet behavior, which is very different from what we learned from the standard theory of renormalization. The coupling parameters scales as the energy. So you have no mixing between the UV and ER. So if celestial holography is right, we needed to revisit the Wilson approach to fundamental physics.
That's, I mean, it's a great question. I mean, in part, it has been discussed in this recent work with Nimar Kani Hamed and Monica Pate and Andy Strominger. First of all, okay, the thing is that in most examples, in particular in gravity, we don't, well, except for string theory, we don't know of any other UV complete theory of gravity, okay? And I mean, the modern point of view in quantum field theory is that one, as you sort of said, is that one thinks about effective field theories, right? But you are saying something about some UV regulator or something like that, but in this EFT kind of point of view, right? Physical observables would not depend on the regulator. They would just depend on some physical scale at which your theory breaks down. So for example, when you have some other very massive particles coming in, it would depend on the masses of the particles you're integrating out or whatnot. That's one thing. And what one can do, and we studied in this recent paper, is to ask, okay, what what does the usual way of thinking about quantum field theory and quantum gravity tell us about these celestial amplitudes? But again, it's a question in which essentially we map properties of momentum space scattering amplitudes, of usual flat space scattering amplitudes, onto statements about the celestial theory. And one thing one can derive, as you're saying, there's going to be, in the low energy effective field theory, one typically thinks about adding higher derivative interactions. But at the end of the day, one can write down a low energy a scattering amplitude in the low energy effective field theory, which is effectively an expansion in powers. So for 4-point function, I'm talking about 4-point functions. It's essentially some polynomial, some expansion in powers of the center of mass energy with coefficients which depend on, well, it's an expansion in S and T, right? But you can reorganize that as an expansion in some energy scale omega, perhaps addressed by logarithms coming from loops. And what one can deduce, so of course, as you're saying, as you're correctly saying, if you have, for example, just mass scattering, the amplitudes on the celestial sphere, they need to know about the full, like they need to know about the UV, right? Because they involve integrals over all energies. So in particular, one can show that for 4-point functions, the 4-point celestial amplitudes are proportional to just Mellin transforms with respect to the center of mass energy. I'm not sure, maybe it's useful to write it down. So say we have some celestial 4-point function. So we saw today that it has to be a function of beta and z, where this beta is essentially a sum from I equal to 1 to 4 of delta I minus 1. And z is this cross ratio, which is the ratio of T and S. Okay, and this can be shown to take the form of a function of z and beta, which is known. Okay, up to this conformally covariant prefactor, but then all that's left is some Mellin integral with respect to some energy scale, the omega, omega to the beta minus 1, m of omega squared times m of m of omega squared minus z omega squared. Okay, so this is just essentially m of S and T. This is the 4-point scattering amplitude. Right?
ST demands 10 parameters. Oh, okay.
Yeah, so S, let me just be clear, if we have some scattering process, P1, P2, P3, P4, S is minus P1 plus P2 squared, and T is minus P1 plus P3 squared. And one can show that Z, if one parameterizes the masses momenta, as I showed in the lectures, this is Z13, Z24 divided by Z12, Z34. And I mean, this, okay, I'm not sure how clear this formula is. Do you have questions about this formula? It's just, it follows, how should I say? This part, I mean, it's essentially the easiest way to see it is that it follows from just putting the 4 external legs in this conformal primary basis. So it's, if you have some if you have in momentum space, if you have an amplitude which goes as m of s and t times momentum conserving delta function of q1 plus q4, right? We said that the celestial amplitude is obtained by taking for massless particles. It's obtained by taking Mellin transforms with respect to the external lines of this A4, including, it's crucial to include this momentum conserving delta function.
Mm-hmm.
And it's an exercise, I mean, you can, using these parametrizations for these momenta, so something like 1 plus zi z bar I, zi plus z bar I, minus I, zi z bar I. One finds that this delta 4 becomes proportional to some delta function, which looks like this, omega 1 minus sorry. Where these are just the ratios of Zij, something like that.
Mm-hmm.
And then you can just do 3 of these integrals. They will saturate these. 3 of these integrals can be done immediately. They will. You can just solve. You can just integrate these delta functions. Okay. So you take this, you plug it in here, and at the end of the day, 3 integrals are trivial, and they will just give some overall dependence on Z, which is gonna, at the end of the day, it's gonna be conformally covariant as it should be. Okay, so there's gonna be this Kij factor I showed, or how did I call it? Khi h bar I of Zi Z bar I. This was this conformally covariant prefactor. There's going to be some dependence on Z, so some Z to some power 1 minus Z to some power for scalars. I'm talking about here just for simplicity. And then all of this is going to be multiplied by 1 remaining. Okay, and there's going to be the delta function Z minus Z bar, which comes from here. And then there's going to be some remaining dependence. So you see that these 3, when you do these 3 integrals, you're going to end up with some factor here, which is going to be just omega 1. So the last integral is going to be the integral over omega 1 of omega 1 to the delta 1 plus delta 2 plus delta 3 plus delta 4 minus 4 minus 1. Does it make sense? It's from essentially just doing this integral. And then there is this prefactor, this thing here. But you can work out that with these parametrizations, S is just S. Upon doing these integrals, you're gonna just find M of omega 1 squared minus Z omega 1 squared. So upon a change of variables, you just find that, I mean, S is an energy scale, so it's gonna be proportional to something like this final omega. Well, S is actually omega 1, omega 2, Z12, Z12 bar, or rather proportional to that. So when you since omega 1 is proportional to omega 2 by the momentum conservation constraint for 4 points, this at the end of the day is just going to become proportional to to some omega squared up to some coefficient, which you can rescale this integral basically. You can do a change of variables, which then just puts the first argument to just be omega, this last energy squared, and this is going to be, but okay, this is just to say that there is, for 4 points, things simplify a lot, and one has a precise formula where, in particular, the celestial amplitude is determined from the 4-point momentum space scattering amplitude by just one single Mellin transform with respect to beta, where we call beta as the sum of the external dimensions minus 4. We already saw that this has to be the case, that this piece has to depend on beta. We saw from Poincare symmetry earlier in the last lecture. Okay, so this is also consistent. It shows that has to be the case. And then you can ask, okay, what are the properties of A4? And as you correctly pointed out, of course, for this integral to be well defined, right, your bulk scattering amplitude has to have good UV behavior. So in particular, if this is just going to be like, I don't know, if this is just going to be, I mean, S to some power P, right? Then this is just going to, or okay, S to some power P would map onto just omega 1 to 2P. Then this integral, you'd have integral from 0 to infinity d omega 1 to the beta minus 1, omega 1 to the 2p, and generically this is ill-defined, right? It blows up really badly as omega goes to infinity. So for say like p positive greater than 1 or something.
Just to check with my back of the envelope calculations, P then is the number of derivative couplings in the interactions.
Right, and now it's this is exactly the point. So now, yeah, this is just the basic observation to say that you need to know, I mean, celestial amplitudes are only well-defined if you have a well-defined scattering amplitude in momentum space. And of course, in most situations, we don't know what this full amplitude is, right, to all energies, right? But nevertheless, one can say some qualitative and also quantitative, one can infer some qualitative and quantitative features of the celestial amplitudes by, first of all, assuming that these amplitudes are relatively well behaved at large energies, right? And then one can, for example, as you're saying, look at some things we know from the low energy effective field theory. Like, for example, we would know that in an effective field theory, this M of S and T has some expansion of the form C and M, S to the N, T to the M, right?
Okay.
At low energy.
So maybe something about the structure, the divergence structure of the amplitude can be also inferred from the generic properties of the celestial amplitudes.
We can infer something about the divergence. By divergence structure, you mean?
Well, the analytical structure and singularities of the amplitudes, or
Yes, exactly. Yeah. So in particular, yes, this is going to be a concrete example where there are some concrete examples where one can infer something conversely. So here I'm just I am mapping some known features. I was about to map some known features about momentum space scattering amplitudes, such as they have this sort of low energy expansion, or that, for example, in quantum gravity, in the hard scattering limit, they would be expected to be exponentially suppressed. Things like that can be mapped onto statements about the analytic structure in beta, so of these celestial amplitudes. So, in particular, the low energy theory you have in the bulk tells you something about the poles in the complex beta plane on the negative real beta axis. So in particular, for example, these coefficients here, which appear in the low energy expansion of the amplitude, can be mapped or related to residues of poles in beta at negative even integer beta. So this analytic structure in the complex beta plane of the 4-point celestial amplitude captures some information about the couplings. So these, at the end of the day, they're couplings of higher dimension operators in low energy effective field theory. Okay, and for example, in the bulk, there are all of these dispersion relations which impose positivity constraints on these coefficients. And okay, we don't know how to derive. It would be cool if there was an intrinsic principle in the celestial theory, which, for example, would reproduce these positivity constraints. So far, what we can do is to, go the known way, that basically Fourier, we're doing a logarithmic Fourier transform of the celestial of the momentum space scattering amplitude, and of course, you're gonna learn some things about, in some ways, this logarithmic Fourier representation of the bulk 4-point scattering, but perhaps we think that there are some principles which govern these celestial theories, which at the end of the day will allow us to say something about the bulk. But so far, I mean, we're just trying to understand what the general structure of these celestial amplitudes is. And to do that, I mean, all we can do so far is to sort of learn by going the direction that, in the direction where we know how to compute things. But going back to Igor's question, I'm not sure if this is what you are, I'm not sure if I'm answering. You said something about the Wilsonian. I think that I'm not necessarily, I mean, I don't know, here the celestial amplitudes involve integrals over all energies. So I don't know, it's hard to think about Wilsonian.
Yes, this is exactly the integral I was thinking about. Science to be UV, well-behaved, some kind of regulator or soft of this integral would be needed. So this is why I asked if there would be some constraint on the celestial amplitudes if you require ultraviolet, well-behaved. So there would be let's say, a mixing between the infrared physics and ultraviolet physics, say in more imprecise terms. But you've explained very well. I am satisfied.
Okay, but just regarding this one, I think just to say again, perhaps here we don't want to put any we don't want to regulate these integrals. I think the point of view one would want to take is, well, my point of view, I guess, is that the celestial amplitudes, we're not sure. Maybe, maybe all of this is just nonsense, and the celestial holography is not going to make any sense, because scattering amplitudes, if we are all powerful and able to compute them in the bulk, maybe they will just be. But we already know that actually in quantum gravity, they cannot be that exponentially suppressed at high energies. So that sort of principle, these kind of bounds coming from high energy and from, for example, expected high energy behavior, for example, from black hole creation or exchanges of an infinite number of states and stuff like that. So those are expected to lead to amplitudes which in the EV are exponentially suppressed and exponentially soft, which already suggests that this Mellin amplitude, which you have to take the integral, you don't want to impose a cutoff because that would break Lorentz invariance, but it suggests that the amplitude, the celestial amplitude is going to be a well-defined object. And perhaps what one would want to do is to take the celestial amplitude as the fundamental observable and impose that, it has to be something which is well-defined. And then that already by itself is going to impose some constraints on the momentum space gathering amplitudes. Okay, I'm not sure if what I said, clear.
Oh, that's perfect. Thank you. I have tried to do this back in the envelope calculation myself from your last lecture, but you nailed it down very well, my point. If you try to do the opposite then, instead of starting from a theory in the book and trying to map to the celestial sphere, you start analyzing the theory in the celestial sphere, the CCFT, and instead of inserting a regulator that might break Lorentz invariance, not might, will break Lorentz invariance, why not to consider instead of celestial spheres, Riemann surface with higher genus, let's say, topological defects?
Well, let me just make a comment before. So this will be the last question, and in a few moments we'll have to switch. So please.
I'm sorry. I will lower my hand.
Yeah. Okay. Yeah, it's a very interesting question. I mean, I think that ultimately, yes, perhaps we have to understand what happens when the sphere is promoted to what becomes some arbitrary higher genus surface. And we discussed a little bit on Slack, but for example, if you look at scattering in 2-2 signature, one can see by studying the conformal compactification of Minkowski space in 2-2 signature that this celestial sphere I mentioned many times becomes a celestial torus. And a completely different story is the story about cosmic strings and accelerating black holes piercing the celestial sphere, where there was some conjecture by Sasha Zhiboyedov and Andy Strominger that perhaps in that situation, the celestial sphere is going to turn into a torus. Okay, it's all, I think, the implications of these kind of higher genus Riemann surfaces have definitely not been explored. I mean, I've tried a little bit, but I think there are more basic things we don't understand, essentially.
Right. Okay, thank you very much. This ends my questions for now. So thank you.
So,
Thanks for
Igor, thank
questions.
you, Ana Maria, for all her contribution to this school and to the very interesting set of lectures and additional discussions and comments during the discussion sessions. So let us thank Ana Maria once again.
Congratulations.
And I think we now all ready to well, for those who are interested in this topic, so we're all prepared to listen to lectures in strings next week or in 2 weeks from now. So if there's still something, you can go back to our recordings and check the details in the lectures of Ana Maria. Thank you very much.
Yeah, I also want to take this opportunity to thank everyone, the organizers for the invitation, and the students were very active on the Slack and asking questions. So, and I'm also very happy to answer any more questions. If you think about anything, even in the future, feel free to email me. So, or ask more on Slack in the next, days.
And let me thank you for the patience, for answering the questions very nicely. Thank you very much. I appreciate, and for the organizers. So, bye.
Okay, very good. Thank you.